Hey everybody, it's Thursday, December 3rd, and as you can see here in the aim today, our focus for today's video is going to be to talk about gravity. Before we get to that though, I would like to review the answers for the worksheet that was posted yesterday. So yesterday I posted a worksheet about an experiment that we usually do in class every single year. It's this tabletop Atwood's machine. And in this experiment, I asked you basically to design an experiment to measure the mass of the hanging object, which is labeled as M2 in this diagram. And so part A asked you to draw the free body diagram, and part B asked you to derive an equation for the mass of the hanging object. Now, the obvious question here is, why am I asking you to do this? And the reason is pretty simple. The experiment is essentially defined by the equation. And so if you have an equation for a variable, designing the experiment is fairly straightforward, because you just have to measure the things that are in the equation. So let's talk about the free body diagram. We'll start with the object on the track. As we've mentioned so far when we're drawing free body diagrams, the easiest thing to think about when you're drawing free body diagrams is the number of forces in the free body diagrams is usually the same as the number of objects the object in question is interacting with. So all we have to think about really is what objects are M1 interacting with. M1 is interacting with the string. That's going to produce a force of tension. It's interacting with the earth. That's going to produce a force of gravity. And it's interacting with the table. And so that's going to produce a normal force. Now, sometimes the table or tables or surfaces in general will produce two forces, a normal force and a friction force. But here it's not going to produce a friction force because, as we've said here, we've got basically a frictionless track. And so the free body diagram for M1 should look like this. We have our force of tension going to the right. That's going to cause the object to accelerate to the right. We have our normal force going up, and that's going to be equal and opposite of the gravitational force, which is coming down. So notice in the vertical direction, these forces cancel each other out. Horizontally, we only have the force of tension. And so the force of tension acting to the right is going to be responsible for the acceleration of this cart. Moving on, looking at M2, M2 is our hanging mass. M2 is interacting with two objects. M2 is interacting with the string, which is exerting a force of tension on the mass. And M2 is interacting with the earth, which is going to produce a gravitational force acting on M2. And so the free body diagram for M2 should look a little something like this. And I would imagine this part of it was not hard for you guys, especially after the Atwood's machine experimental, or not the experimental design question, the other free response question from the beginning of the week, because this is exactly the free body diagram for one of these objects in those problems. So we have a tension force going up, we have a gravitational force going down, and because the block is accelerating down, I guess I didn't put that vector anywhere, but because the block is accelerating down, well, we have to have the weight vector being larger than the tension vector. Also, there was no grid space here, but I just want to be clear that the length of the tension vector in this diagram should be about the same as the length of the tension vector in this diagram. It actually doesn't look like it in this picture, but I did measure it using a ruler, and so they are actually the same. I think it's just because they're pointed in different directions. They don't look quite the same length, but that's the idea. And so this is what your free body diagram should look like. Now, of course, part B to this question asked us to derive an equation for the mass of the hanging object, M2. And the way that we derive that equation is by using the equations that we obtain from the free body diagram. So looking at M1, the equation for M1 is pretty simple. We take MA, And of course, because we're talking about m1, we're going to take m1a and set it equal to the forces going in the direction of the acceleration, that's ft, minus the forces that are going opposite the direction of the acceleration. And in this case, there are no forces going opposite the direction of the acceleration, so the equation we end up with is just m1a equals ft. Pretty straightforward. For m2, again, we take ma and we set it equal to the force going in the direction of the acceleration. That's going to be m2g. And then subtract the forces going in the opposite direction of the acceleration, which would be ft. And so for m2, we have m2a equals m2g minus ft. And that's our equation for m2. And I feel like I've said this 100 times already. I hope you guys are starting to internalize this. Without question, the easiest way to combine equations when you are trying to deal with a situation where there's a string is you add the equations. That'll get rid of the force of tension. I hope you thought about this a little bit and realized that getting rid of the force of tension is actually really useful for this kind of problem because it's hard to measure. You'd have to attach a force sensor in the rope, and it just like turns into a nightmare. And so to combine these equations, we add them. And so notice adding the equations, literally stacking them on top of each other and adding them. On the left-hand side, you literally just have the sum of those two terms. So that's going to be m1a plus m2a. And on the right-hand side, the tensions cancel, and we're just left over with m2g. It's just the weight of that hanging object. And so now notice what's a little annoying about this equation, but not overly complicated, is we have an m2 term on both sides of the equation. So the first thing I definitely have to do here is I have to gather all of the m2 terms on the same side of the equal sign. And so I do that by subtracting m2a over to the other side. And now that I have m2 in both terms on the right-hand side, I can factor it out. And so when I factor it out, I get m2 times g minus a on the right side. And then, of course, I still have m1a over here on the left side. Now all I have to do to solve this for m2 is divide by the term g minus a. And when I divide by the term g minus a, now I've got my equation fully solved for m2. That's m2 equals m1a over g minus a. And that's it. That's my equation for m2. Now, again, the reason why we want to do this is because according to like basic principles of experimental design, the way you design an experiment is you just talk about how you would measure stuff that's in the equation. Shouldn't be all that hard to figure out here. To measure the mass of object 1, we're just going to use a triple beam balance. Piece of cake. G is a number we know. Measuring the acceleration, on the other hand, could be kind of tricky. But if we go back to the list of materials that we had, notice here we have meter sticks, stopwatches, photo gates, motion sensors. It is just a fact, whether you realize it, that although you could use a meter stick and a stopwatch to measure the acceleration of the cart, and you could use the equation a equals 2 delta x over t squared, as long as you start the cart from rest, that will work. It is by far the easier move to measure the acceleration with a motion sensor. Measuring the acceleration with a motion sensor is actually even easier than doing it with photo gates. Because if you're going to measure acceleration with photo gates, you have to use multiple photo gates. Measuring it with a motion sensor is really easy because all you have to do to measure the acceleration with the motion sensor is just put the motion sensor behind the cart. And so like here's our general setup. We have the pulley, the string, there's our hanging mass. We've got our cart over here that the string is attached to. This thing's got wheels. The motion sensor is like a sonar device, remember. And so this thing is going to be sending out sound waves. In the lab, and it's unfortunate that you guys can't see this stuff in person yet, But in the lab, we actually have these little magnetic targets. It's like a fin almost that attaches to the back of the cart, which makes it really easy for those sonar waves to bounce off of the cart. And in our lab computer program, we have the option for this thing to produce a velocity versus time graph. And so when this thing produces a velocity versus time graph, we're just going to, and it's pretty cool because you can just drag a certain interval of the line and boom, it'll spit out the slope instantaneously. The slope is going to be our acceleration. And so we run that back for a few trials and that's what we're going to measure. And so notice here in my chart, what I wrote down for the stuff we're going to measure is I said, well, we're going to measure the mass of the cart plus the added masses with a digital scale or triple beam balance. And I'm going to measure the acceleration of the system using a motion sensor. Again, you have the freedom to choose to do this however you want. If you wrote you were going to measure distance using a meter stick and time using a stopwatch, and then you're going to calculate the acceleration using the equation 2 delta x over t squared, that's fine. Remember, the scoring guide, if this was an experimental design question, would say something to the effect of like, any procedure which reasonably gives the students a reasonable method to reasonably measure the acceleration of the system. So like they give you a lot of leeway, and it is reasonable to measure the acceleration of the system using those sort of more primitive tools. That said, you make your life a lot easier in terms of the section that says like, how are you going to analyze the data? You make your life a lot easier in that section if you simply say, well, I'm just going to get the acceleration from the sensor. It's a lot easier than having to talk about, I'm going to take the distance information and the time information and calculate the acceleration and do that for multiple trials and then average that together. And so I want you to just keep that in mind. Motion sensors are capable of spitting out position versus time graphs and velocity versus time graphs. And the computer program that the graph is imported into enables you to just highlight a section and calculate the slope. Now, I would show you how to do that literally on this video if I could, but school is closed, and so I don't have that lab equipment with me here at home. And so as soon as they open the building back up, which it looks like it'll be after Christmas, I will actually film this experiment and show it to you just so you can get a sense of how this works. All right, moving on. As you can see here in part D, it says which quantities must you plot on the x-axis and the y-axis to produce a graph which has a slope which will be equal to the mass of the hanging object. Now, the equation that we just got here from our derivation is m2 equals m1a over g minus a. Now, this looks a little funny, but this equation does take the form of delta y over delta x, where everything that's in the numerator should be plotted on the y-axis, and everything that's in the denominator should be plotted on the x-axis. And so when you plot m1a on the y-axis and g minus a on the x-axis, sure enough, you get a graph with a straight line. And when you calculate the slope of that graph, the slope of that graph will, in fact, be equal to m2. Pretty cool. So for the answer key there, I just wrote, you plot g minus a on the x-axis, you put m1a on the y-axis, and you're in business. That's the basic idea behind part D. Anytime a derived equation or an equation from the reference table works out to be a fraction, just plot the numerator on the y-axis, the denominator on the x-axis, and you're in business. That's the point. All right, moving on to part E. Part E says, in order to produce the graph we'll need to produce, the graph I just discussed, we'll need to vary quantities. That's because you want to produce a graph with multiple data points for you to calculate the slope. Now, some of you seemed to kind of miss this point with the friction lab experiment, and you only did 2 different masses, and so you only had 2 data points. You get a much better line of best fit, especially in real world experiments when you use multiple data points. And so in order to produce the graph we need to produce, we need to vary quantities. And I hope everybody realizes that the main idea is, looking at the equation, the only thing you can do is vary the mass of M1. I have a feeling that it is possible that some people said, oh, well, all we'll have to do is vary the acceleration. Piece of cake. But the acceleration of the system, if we're going to keep M2 constant, which we are, the acceleration of the system is dependent on M2, which is a constant, G, which is a constant, and M1. And if we don't want the acceleration to be constant, we got to change M1. And so what I wrote here is, in order to produce the graph that we'll need to produce, we'll need to manipulate M1, the mass of the cart, by adding masses to the tray on the cart. If we increase the mass of the cart, which we're calling M1, we should expect to see a decrease in the acceleration of the system, since the new system would now have more inertia. I hope everybody realizes that. So we're going to have a different M1, we're going to have a different acceleration, but the value of M2 is not going to change. And so we should expect, to some degree, to see these things change in some proportion, so that whatever the new M1 is and whatever the new acceleration is, well, that when you take M1 times A and then you divide it by G minus A, that you get the same value for M2, or approximately the same value for M2. And so that's the idea. Now, I'm going to leave this up here for a second. I'd like you to pause this video if you'd like to amend your explanation or just write this down. And when you hit play, we'll move on. Okay, so moving on here for part F, this is the part that's a little tricky. It says here, as mentioned in the initial description for this problem, the cart and the track system we bought at school is marketed as quote unquote frictionless. But obviously that's not completely true. There is a little bit of friction. And so the big question here is, well, how will the presence of a small amount of friction affect the measured value of M2? And it says here, answer this question without doing any math. And what I wrote for the hint was, break this down into smaller problems. The presence of friction will obviously affect one quantity in particular. That's supposed to be a period after that. Which quantity? How will it be affected? How will that quantity being affected affect the measured mass of the hanging object, M2? And so to do this properly here, you're going to need to take a real close look at the equation. And so let's just take a second, take a real good look at that equation. Now, looking at the equation here, we can see that the value that we measure in our experiment for M2 is going to be based on M1 and A. G is a constant, so that's not going to change. And I hope everybody realizes friction is obviously going to have no effect whatsoever on M1, because it's just a mass. Friction obviously is going to affect the acceleration. And so the big question here is, how will friction affect acceleration? And it should be clear to everybody that if M1 is sliding along the surface and all our model has accounted for is the force of tension, the fact that there is a teeny tiny force of friction acting on the cart means whatever we calculate for the acceleration or like whatever we would calculate for the acceleration using this model, the actual acceleration is going to be a teeny bit less. That's an important thing to realize here, that friction is going to affect the system by making A, the acceleration, smaller than theory predicts. And so the big question that we have to answer now is, how is the fact that A is going to be smaller, how is that going to affect M2? And if you go through each part of the equation, it's actually pretty interesting the way that works out. M2, according to this equation, is proportional to the product of M1 and A. And so what we can say here is that if A is smaller, M1A is smaller, and because M1A is proportional to M2, M2 would be smaller. Also, though, the equation says that M2 is inversely proportional to G minus A. And so now we have to work our way through that. Well, looking at this part of the equation, if A is smaller, then whatever G minus A is actually going to be bigger. Right? Let's round G to 10 for the purposes of this argument. If A is supposed to be 3, then G minus A would be 10 minus 3 is 7. But if the acceleration is actually 2, because friction's acting on it and we're ignoring that, then G minus A would be 10 minus 2, which is 8. So if A is smaller, then that means G minus A is bigger than it otherwise would be if there truly was no friction. And here's the deal. If the acceleration being smaller means G minus A would be bigger, since G minus A is inversely proportional to M2, that means M2 would be smaller also. And so the acceleration being smaller on both accounts, both spots where the acceleration is in the equation, the A being smaller would make the measurement of M2 smaller. And so this is an interesting little insight into the way we usually do error analysis in physics experiments, because if we would expect friction to be a big deal, then what we would expect to see is the mass we measure experimentally to be slightly smaller than the mass actually is. And if we do the experiment and we see that, then we get a pretty good sense that the reason why it's smaller is because of friction. And so for this question, what I wrote is the presence of friction will obviously affect the acceleration of the system by making it smaller than it would be in theory. The mass of M2 in theory is given by the equation M1A over G minus A. So the mass is proportional to A over G minus A. A little bit of a weird way to put it. If the acceleration is actually a bit smaller than it would be without friction, the numerator would decrease and the denominator would increase, which both would contribute to M2 being too small. Friction would cause our measurement of M2 to be smaller than the actual value. Again, this is a little bit complicated, especially considering that this is the first time we've really talked about it. this year. So I'd like you to take a second to pause this video here and write that down or amend your explanation to include anything you might have missed. And when you hit play, we'll move on to the next part. All right. Part G, as you can see here, so I'm just going to keep it in this window, says, how can we limit experimental error in this experiment? This wasn't really a trick question. Remember, an easy way to talk about limiting experimental error is to just talk about doing trials. It's an easy point. And so I wrote here, we can limit experimental error by varying the mass as much as possible to produce more trials. It's also important to realize if you wanted to be really nuts about it, not only could you use like 10 different masses for M1, you could also, for each individual mass, do multiple trials there and average them together. So like, let's say you do the cart by itself, you do 3 trials, you average the accelerations and call that the acceleration. Then you add 100 grams to the cart and you do 3 trials of that, average them and use that as your acceleration, and then keep doing that for all the other additional masses. What I also put, just for fun, just an interesting little thing to think about, is you could also just do a drag test if you really wanted to, and we could measure the coefficient of friction and then just account for friction in our free body diagram. And I think the idea is if friction was significantly affecting our measurement, making M2 too small, then by accounting for friction, it would be closer to the actual value of the mass. Okay, now just very quickly before we go, I want to show you some data because I'm a little bit of a lunatic and I like to avoid absolute failures in front of my students. So I usually try the experiments out a couple times before I have my students do them, just to make sure that they should work. And so I did this experiment a few years ago, and so I actually have the data still saved on my computer. And so notice here, the mass of the cart that I was using was 299 grams, or 0.299 kilograms. Notice none of my stuff is labeled great because I just was trying to do this quickly. And the mass of my hanging mass, which I was trying to find, was 200 grams, or 0.200 kilograms. So notice I did this first without adding any masses. I measured some accelerations. I averaged them together for my average acceleration. I actually showed a little bit of a calculation over here too, to just see what would I get if I just calculated the acceleration from that trial alone. And so notice I added some masses, and then I measured some accelerations, averaged them together. Now I've got a bunch of data points. I did this for 1/4 of a kilogram added, 1/2 kilogram, 1 kilogram, and then 1.5 kilogram added. So these are my total values for the mass of the cart system. And when I went ahead and plotted my data, remember I needed to plot M1A on the y-axis and G minus A on the x-axis. So notice as the acceleration gets bigger, M1A changes as we would expect, and G minus A as well. Or I should say, as the acceleration gets smaller because the mass gets bigger, notice the change in the acceleration. Notice the acceleration here is decreasing. You would think might make M1A smaller, but the fact that the mass is going up by so much actually makes M1A bigger. And here, notice the acceleration being smaller makes G minus A smaller. Geez, I said it backward again. It makes G minus A bigger. A G minus a smaller number is going to be bigger. And so when I plotted my data, that's what I got, a slope of 0.195. Again, I decided, just for the purposes of this experiment, to use exactly a 200 gram mass, or 0.200. And so the fact that I got 195 means for this experiment, my percent error was about 2.5%. Not bad for only a few trials. Notice I also discovered something interesting. There's a weird jerk that the object experiences right at the beginning before the force really acts constantly, the force of tension in the rope. It kind of experiences a sudden increase in the beginning, or at least as is captured by the sensor. And so as I wrote here, a little note, make sure you tell the kids to grab the acceleration value from the graph way after the exponential increase part in the beginning, because that actually corrupts your data a little bit, as I discovered once I started to tell kids to do that. They got data that was much better, which I thought was an interesting little result. Let's move on to gravity. All right, so the first big question that we have to ask when we're talking about gravity is, what are the factors that are going to affect the gravitational force between two objects? So in this scenario here, we are assuming that we have two objects. And we are trying to figure, well, what about these objects is going to affect the amount of gravitational force that these objects experience? Now, you guys have already seen this before, so I'm sure you remember. But the amount of mass that the objects have, it would make sense, affects the amount of gravitational force that they exert on each other. Also, it makes sense, I think, the distance between the objects is going to have an effect on how much gravitational force they exert on each other. So I'd like you to write this down. Gravity, remember, is a force of attraction between all objects with mass. And we can see from basic experimental relationships now, but as Newton realized way back in his day, by just thinking about it, that if gravity is an attraction of objects with mass, well, it should make sense that if they have more mass, then they're going to attract each other more. But if they're farther apart from one another, then they should attract each other with less force. Take a second to pause this video and sketch this diagram here. It's good relationships established by this diagram, and when you hit play, we'll take a look at the equation. Okay, so Newton's genius was in being able to figure all of this out by just thinking about it while using a small amount of astronomical experimental data. But what Newton realized is that if the mass increasing is going to make the force increase, then that means the force of gravity is directly proportional to the masses. Additionally, what he realized is that if the distance being larger makes the force smaller, then the force should be inversely proportional to the distance. Newton's real genius was in being able to use a bunch of astronomical data about the motion of stars and planets produced and really described in great theory by a guy named Johannes Kepler, who's famous for Kepler's laws of planetary motion, which we will briefly discuss a little bit this year. By looking at Kepler's data and Kepler's laws, Newton realized that the only possible way that the distance could figure into this equation is for it to be squared. Newton actually derived his universal law of gravitation from Kepler's laws of planetary motion, which is pretty cool. We're actually going to see how that works later on this year. But if you're ever wondering why the r squared comes into this equation, it's because Kepler said, and this is a bit of an oversimplification, but it's because Kepler said objects that are in orbit, where the force of gravity is causing them to orbit, can only orbit in elliptical orbits. And so because of the elliptical nature of these orbits, as it turns out, Newton discovered that the force of gravity is not inversely proportional to the distance, but rather the distance squared. And so his equation in its modern form looks like this. Fg is equal to g m1 m2 over r squared. It's important to realize here, I'm just going to say this because I feel like people are usually confused about it. The g is in the numerator. Writing it off to the side or not, it means the same thing as this. And so that's an important thing to realize. Notice here, they have the force of gravity in absolute value brackets The only reason they do that is because the force of gravity is subject to all of Newton's laws. And so there's always an action-reaction thing happening here. And so to some degree, there really is no such thing as a gravitational force. There are always two gravitational forces. The Earth is exerting a gravitational force on me, and by Newton's third law, I am exerting a gravitational force on the Earth. And so whichever way you slice it, one of those has to be negative because they act in opposite directions. And so that's the reason why the absolute value sign is there. I'm never going to use that in my problem solving. You shouldn't either. I just want you to know why it's there in the AP reference table. And so M1 in this equation is the mass of object 1. That, of course, is going to be measured in kilograms. M2 is the mass of object 2. Also measured in kilograms. R is the distance between the center of each object. Now, this matters for big things like planets, because that's where the center of mass of the planet is located. And when, something like the Earth, which has a radius of like 6 million meters, it actually is going to make a difference whether we use the surface of the Earth or the center. And that distance between the centers of the objects is measured in units of meters. Fg, of course, I always use an uppercase G for the most part for this equation. It doesn't really matter, though, is the gravitational force. Measured in newtons. And big G, the universal gravitational constant, is 6.67 times 10 to the negative 11. Now, the unit is printed in the AP reference table different than it is printed in the Regents reference table. So I just want to talk about this for a second. Notice, if you solve this equation for big G, you get Fg r squared over m1, m2. And what we write in the honors, or whatever, the Regents reference table, we write Newton meter squared per kilogram squared. The meter squared coming from the squaring of the r, and the kilogram squared coming from the product of m1 and m2. That's not what it says in the AP reference table. The reason why is because they break down the Newton as a kilogram meter per second squared times a meter squared over a kilogram squared. And so what they write in the reference table is a meter cubed per kilogram second squared. Yeah, I know. It's a little annoying. It is what it is. But I think it's important to realize if you just write Newton meter squared per kilogram squared, that's totally cool. I just want you to understand when you look at the reference table and you see the number and this monstrosity, you know that's why that unit is there. It's because in the unit Newton meter squared per kilogram squared, they've decided to break down the Newton by using Newton's second law to call a Newton a kilogram meter per second. And that's it. Now, I want to take a second to talk about the universal gravitational constant, because the purpose of this course, compared to the honors course, is for you to really try to understand this stuff and understand how it works, why things are the way they are. So a good question here would be, well, why is the universal gravitational constant 6.67 times 10 to the negative 11? And the answer is pretty simple. We have no friggin' idea why. It's that number. But we do know how to measure it. An obvious question here would be, how could we design an experiment to measure G? Well, we've beaten this into the ground already at this point in the year, and we are going to continue to do that. But the equation is the key to the experiment. And if we make a graph where we plot FG times R squared on the y-axis and we plot M1 times M2 on the x-axis, we should get a straight line on the graph where the slope is equal to big G. Now, how exactly are you going to do this in the 1700s? Well, the experiment was done by a man named James Cavendish. This experiment is famously referred to as the Cavendish experiment, if you would like to Google it. Here's a brief video representation of it. So he basically took these two super heavy objects, these big lead balls, and he put them next to two extremely light objects. And what he did was he moved these big heavy objects closer and closer and closer to the lighter objects. And what he realized is that if he attached the light objects, and I'm going to go back and see if they show you a side view here, if he attached those really light objects to a fine string, then when these very, very light objects were attracted to these heavy objects and they were free to move, they would turn the string. And by turning the string, he was able to figure out the amount of tension in the string that was caused by the attraction. This is pretty genius. And by figuring out the exact angle the string turned, now notice this representation of it is showing you how you could do it with a laser. This is how the experiment has gotten a bit modernized. But the basic idea is by figuring out how much the string turned, you could measure the force of gravity between the objects. It should be clear to everybody that simply by looking at the masses, we could measure the distance between them. And by measuring the masses of them, like using a triple beam balance, we could figure their mass. This is actually how he figured out the value of big G. When he did this experiment way back in the 16 or 1700s, I forget exactly when this was. You could look it up, though, and see. When he did this experiment way back then, he actually measured big G, the universal gravitational constant, to within 10% of its accepted value today, using lasers and all sorts of fancy experimental equipment, which is pretty cool. These numbers, these physical constants, are not made up. They are determined experimentally using the ideas that we've discussed so far this year. All right, I have a feeling this video here is getting kind of long, so I just want to take a quick look at some problems for today, and then we'll call it a day. So let's take a look at a basic example here. It says, determine the gravitational force, the average gravitational force acting between the Earth and the Moon, if the average separation distance between the Earth and the Moon is 3.84 times 10 to the 8 meters. Now, as you saw on Google Classroom today, I posted a handout with values of mass, distance, orbital distance, radius, whatever it is, for different planets from the textbooks we use in the packets. You will see these values in some of these textbooks printed slightly differently. It's just because they get slightly different values from different experiments, which are done at different periods of time. They all agree with each other to at least two significant figures. So we're not going to go too nuts about the discrepancy in all these numbers. I just want you to keep that in mind. So this question is asking you to determine the gravitational force. So they tell us here that the Earth has a mass of 5.972. See, I know the mass of the Earth is 5.98 because that's how it's printed in the reference table, but you don't have to worry about it. Times 10 to the 24 kilograms. The mass of the Moon, they say, M2, doesn't really matter which one you call M1 or M2. Generally, what I do is just list them in the order they're said in the problem. M2, the mass of the Moon, they say is 7.348 times 10 to the 22. R, the average separation distance between them, they say, is 3.84 times 10 to the 8 meters, or 384 million meters. Big G, of course, is 6.67 times 10 to the negative 11 meter cubed per kilogram second squared. And we're looking for Fg, the force of gravity between them. This equation is a basic plug-in. That's really all there is to it. I hope everybody realizes that. We plug in our number, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. M1, 5.972 times 10 to the 24 kilograms times M2, 7.348 times 10 to the 22 kilograms. And we divide all of that by 3.84 times 10 to the 8 meters. And then we square that whole thing. Now, I want everybody to realize the point of me showing you this calculation is not just showing you this calculation. You used to know how to do this in honors physics. The point of me showing you this calculation is to make sure you remember how to put it into your calculator. I like to put things all in my calculator at once. The way I do it is I put an extra set of parentheses around the numerator. So I put parentheses, parentheses, to my numbers, and then when I finish typing the times 10 to the 22, double parentheses again, and then I close this up in its own set of parentheses. Your calculator doesn't know PEMDAS. You want to idiot-proof it for your calculator. And when you do that math correctly in your calculator, so make sure you can do this. If you're having issues with your calculator, let me know. You get 1.99 times 10 to the 20 newtons. Now, how do we end up with newtons? Well, a newton is a kilogram meter per second squared. And so notice, there's supposed to be a seconds there. That's kilogram per second squared. This kilogram cancels one of those kilograms. That leaves behind my kilogram. My meter squared here cancels two of those meters, leaving behind just one. And then that's kilogram over here, meter per second squared, thus giving me the newton. And that's it for that calculation. These problems are basic plug-in problems. If you make sure you plug them into your calculator correctly, you're good. Last thing I want to do for today, real quick, a problem we've already seen before so far this year, is a question that looks like this. It says, how would the force of gravity change if the separation distance between the Earth and the Moon doubled? Notice their usage of the term doubled. What kind of problem is this? Well, you could just take the distance given in the problem, 3.84 times 10 to the 8 meters, double it, and do that whole big, long, disgusting calculation again. But we already have a method for doing these problems when they give us hypothetical changes in variables. That method, remember, is the 1-1-1 rule. So we can say r prime here is 2r, and Fg, as we calculated, is 1.99 times 10 to the 20 newtons. We're looking for Fg prime. And so we write our original equation, Fg equals g m1 m2 over r squared. Then we write our primed equation, Fg prime is g m1 m2 over 2r whole thing squared. That gives us Fg prime equals g m1 m2 over 4r squared, right? Because 2r times 2r is 4r squared. And then we simply rewrite this by pulling the whole numbers out on the outside. So we pull out a 1 from the top, a 4 from the bottom, and that means Fg prime is 1/4 of Fg. Now, notice here, I wrote an equal sign. And the basic idea here is because we actually know the value for Fg, we can just literally take 1/4 of that. So we would take 1/4 of 1.99 times 10 to the 20 newtons, and that would give us for our Fg prime 4.98 times 10 to the 19 newtons. So if they ask you what would the new force be, you could do this. Notice the question here says how would it change? It would change by 1/4. And that's the idea. The 1-1-1 rule, you will see in the next couple days, really comes up quite a bit in gravity problems. So if you felt like you didn't really have that down after the last test, make sure you get this down now. Because the way I see it, a 1-1-1 rule question on the AP test that's multiple choice is a gift in terms of giving you points that you can just throw in the bank. All right, everybody. That is it for today. Have a good one.